It's my great pleasure to introduce José Castaños. Dr. Castaños joined IBM Research in 2000 after receiving his PhD in computer science at Brown. His initial assignment as a research staff member involved the development of parallel applications for high-performance computing. He later became one of the technical leaders of the Blue Gene L system software and managed the Blue Gene P software team, working on many of its components, integrated software development environments, simulators, kernel, runtime libraries, and management infrastructure. Blue Gene became the fastest supercomputer of the world in 2004, holding that position for 3.5 years. In 2009, the US government awarded IBM with the Medal of Technology and Innovation as a result of the scientific breakthroughs provided by this architecture. After Blue Gene, Dr. Castaños led a research team to tackle the optimization of scripting languages. He is currently a systems architect of OpenStack Cloud Technologies at IBM Research. He received his undergraduate degrees in systems analysis in '88, operations research in '89 at the Universidad Católica in Buenos Aires, Argentina. And I'm not sure why he doesn't have this on his official bio, but he was also a TA for my operating systems course back in the '90s, and I remember him very well for that. Jose.
So can you hear me well? Thank you. So since I left Brown, I joined IBM, we work on a variety of supercomputing projects, and we have made machines of all shapes and colors, basically, you can imagine. So we have some machines, for example, that are really nothing more than PCs connected with a fast network running Linux. And then we have machines, for example, like the Blue Gene Cyclos that are more esoteric machines, more like new architectures with new instruction sets, not conventional at all. Some machines, for example, are actually based on very low power, very efficient low power processors. Some machines are very big, high-end processors, basically big fat nodes, basically, with a lot of memory. Some machines are actually using a very low degree, low-level network or low-level interconnect, very simple interconnect. Some other machines, for example, are actually built with a very fast, very powerful network to do communication between the different nodes. So we have actually been able to play around and build all of these machines. We have a variety of customers, mainly from the US government and mainly from the academia universities, but also some as practical companies buying it. Some of these machines, for example, I can mention here, for example, the Roadrunner was actually built using game processors. It was using the cell processor is the one that used for the Sony PlayStation 3. And that one also had a hierarchical kind of like a node. So really it's not just one type of node, but several more powerful nodes and less powerful nodes. This hierarchical memory is something that John also was working on with hybrid computers, basically, while I was here at Brown on the fence. So, but here I'm not just to sell you computers, and if I wanted to sell you, I don't think you would buy it. There is a reason why Tom didn't mention the IBM Cave or the IBM SP2 when he actually mentioned the original system. It was basically like one IBM computer that didn't go very well here at Brown, but was good for my thesis. So here I'm more just to give you an idea of what the things I learned here at IBM helped me and help the team to build these computers on the real world. Okay. Now, when we started, for example, Blue Gene, the computers that you would build, the big supercomputers, would be built by just picking the biggest workstation you could buy, the same ones that Tom was mentioned before, put it a fast interconnect, put a high-end like operating system, Unix, that kind of thing, and then call it supercomputer, and that was basically what all the ASCII computers were built around. When we started this project, we started with the idea that we have a rack. A rack would be like a refrigerator, and how much compute power you could actually put in a more efficient way. And there, we know that a rack can cool basically with air about like 25 kilowatts. If I can put 1,000 nodes in that machine, then it means I could actually like build a 1,000-node computer, I mean a lot of compute power, but it needs to also to be very low power. I cannot put like very expensive nodes on the things. That means if I'm spending about $100 basically to building that compute node, then I cannot spend a lot of money to $1,000 to build like a very complex interconnect. I cannot give them a lot of memory as well, because if I have like spent $1,000 on memory on interconnect, let's just use a bigger, fatter node that you have. So because of that one, we are limited on the kind of networks that you could actually build. The networks that we actually build, basically we chose like a network like a 3D torus on a 3D mesh, because really it's a very simple network, and we could actually build more and more and more and increase the sizes of those machines as much as we actually wanted it. If you look at the project really started with nothing more than just 4 kinds of chips. This special chip, basically, that we actually built and embedded a low-power processor. It had embedded memory as well for DRAM on the chip. DRAM, standard DRAM, a special kind of like chip to do the connections, where I mentioned it before, and then one FPGA that was actually used for management. And that was just it. I mean, the whole machine was basically like making multiple copies of exactly the same architecture. And on the biggest system, we actually put about 100,000 nodes. Basically, is more than a basketball card size of the machine. The third generation, we actually reached about almost 2 million cores, basically, to actually get on that in that machine. But again, based on the same principle of a cellular architecture that you actually can increase it. This 3D mesh and 3D torus works well for a lot of scientific problems, because they're actually based on simulating some physical phenomena. You are simulating the weather, you are simulating, for example, like a reactor, or you are simulating molecular dynamics, like biology. Everything is localized. You only need to communicate to a few of the places, a few nodes around, so you don't have a lot of problem on that. Some other problems require much longer degree communication. There is a US government agency that has basically problems called gaps that requires you to do random memory accesses across all the machines. So think that all the machine, the memory is aggregated, and you need to actually read, modify, writes basically on things. That machine is not theoretically good for that kind of things, because all the communication is like a pain. Still, when we actually build the machine, we actually managed to get something called 20 gaps, basically, while all the original performance numbers we actually got on that, on the things similar to the Cray that David was mentioning, were about 2 or 3 gaps. But 20 or that is the maximum we could actually achieve on the things. For a very fast interconnect, right, that you actually want to do it on a machine like this one, you are shooting for something that's for 4,000 gaps. So really, you are spending, on the interconnect most of the money on that setup. Now, when we started the project, this was a 3D mesh, a 3D torus. First task was to actually map a 2D FFT into that particular architecture. We have seen enough FFTs basically in grad school, so it was not something that was difficult for us to do. Done that one, complete. But the problem that we're trying to solve also had some other communication patterns, particularly doing reductions, where all the nodes collaborate to actually get some result. And no matter what we would actually be able to do in that, we could not get basically the time into the budget that we actually do for every one of these iterations. And it was not a problem basically of the interconnect. It was just that in software, we could not get the operations to actually get the packets, produce it, and send it to the next one. So that one was when we actually started playing with a collective network basically and reductions, and doing all the communications for these global operations in the hardware. In the network logic, the architects put a floating point unit or a fixed point unit, and directly they were doing all the operations at the scale. That's what allowed us to actually reach scales fairly easily. The other thing that they did when they do that one is, by the way, let's put a barrier and a centralized clock. So by having one clock across the board, we could actually ignore all the Leslie Lamport kind of clocks and all these things basically that cause a lot of pain. What you really need to have is not drifting between the different nodes, really, and as long as you make the clock distribution tree, it would actually work fairly well, and you don't have to worry basically about the drifting across the nodes. So that's one of the things that we actually put on that communication. So that was basically like things we actually did on that side. The question that we actually had always is that what do you have to do with a torus or a mesh? And you know that you can convert from theory, basically like from a torus to a mesh and run it inside the mesh. And this constant increase on the longest path, in constant decrease on the bandwidth that you would actually have. But then, why then we actually use the torus? Because the torus has a problem that is very difficult to partition. And when you have a machine that is 64 refrigerators, 100 refrigerator size, it's unlikely that you are going to give the whole machine to a single user for the whole time. You're actually going to need to partition it in multiple ways. So really, like in theory, the torus would actually not look particularly well. But if you look at, for example, how this kind of architecture was actually done, think that this place is a mid-plane. A mid-plane would be half of a rack, something like this big, that you actually put 512 nodes on the things. Between mid-planes, we would actually route and put all the cabling, basically, like to go through specific set of chips we actually like built that basically was doing the routing. And the cables would actually go from one of these halves to the next halves on the next things. By just doing and playing basically with the way we're actually doing the connections inside these special links, what we could do is then partition the whole my big machine into sub-units where every one of the units still maintains the properties of a torus, and you can still have a fully connected torus as well. Now, obviously, I'm showing you here just one dimension on just one cable. Think that you have basically 64,000 cables going around basically on the whole system. So you need to partition the whole setup in a much more complex way. It was, again, another mapping example basically that we needed to do to actually do all this placement of the different nodes. And don't think that you also have these long cables, because a cable, from one side of the machine to the other one, you have 50 meters or more basically to go. So they are like cables, like when you actually do the placement into the machine, the floor plan, you actually worry to find the optimal placement to actually get like shortest communications between the nodes. So once you actually decided that you're actually going to put all these kind of like partitions, what we do is we give a user a whole partition to a particular user, and nobody else would actually like be sharing the system with that particular user. That means basically that I can electrically isolate and separate different users and don't have to worry about a user interfering with another user. Everything is isolated. As long as they cannot reach my management infrastructure, then everybody would be isolated, separated. So if that happens, then I just can screw up myself. As a user, I would not be able to screw up anybody else basically on the system on the fence. So that means that nothing to worry about Byzantines or anything that need to worry security, because we take care of the security at the hardware side between nodes. We can put all the communication into the user space and then be done basically, like, allow the user to actually do the communication at much more performance speed that you could actually have. For doing that one, we wrote our own kernel, and the kernel basically has a very small and simple set of calls. I think the original version of the kernel had 50 or so system calls, and most of them were just redirect the calls to some other nodes that you actually have. But then basically think that they start asking you, they say, okay, why don't you add this one, and why don't you add this one, and why don't you add this one over there? I mean, the customers could actually go and ask you, contract, basically, and you actually get the extra functionality. At some point, they ask you, why don't you run Python, basically, on that code it happens to us, basically, on the things. And there means a completely different game. You need to run, basically, a full operating system with shared memory and everything on that one in order to just be able to run Python and things. Good things we were running Linux as well, basically on those compute nodes, so it was not something that changed basically on completely from us. The other thing that was particularly useful is that because you have your dedicated system, we have no interference for system services. There is no checking for a virus basically inside your node when you actually run it that slows down your machine. You have a very deterministic behavior. Once you actually got a performance for a node, you can repeat it, and many runs would actually give you exactly the same performance. And that's something that was particularly useful for the scientists. I mean, the scientists love it that we're able to guarantee them basically to get some performance over and over again on the things. And we actually use a lot of open source code basically on these projects. In all these projects, we actually try to probably like write basically like some of the low-level communication libraries or a driver, and then it's likely to be GCC with Linux, with standard message passing, with all the standard things basically that you could actually imagine on this. One thing that we had to come very quickly good was on simulation environments. Think that basically what you do is you get a chip. The chip new chip comes from manufacturing. They hand deliver the chip from the factory to your site. And then you have all the IBM executives, does it work, does it work, does it work? I mean, so you actually try basically the first thing, there is no smoke coming from the chip. No, so good on that one. And then you start slowly trying to put basically like, functionality to see if the next thing actually works and the next works and the next works. It's not the right time to start writing software at that point. I mean, you better have the whole software running, and you actually be sure that it works, because at that point you don't know if the chip is not working or if your software is not working, basically on things. So we actually have a bunch of like simulation environments, basically. Some simulation environments basically would be just by having the design of the chip. You actually like run it on a VHDL simulator just to get a prompt, basically, at least a week, basically, before you actually see a prompt, because that's how much it takes you to boot. We have supercomputers that do the simulation of the gates, basically, as well, mainly like some of them built on FPGAs, for example, that would give you like 6 to 8 hours, you would actually get basically the prompt to actually get running. And then, but this one with just one chip. We're actually building it for like, a bunch of things, several thousands of those machines. So we have a bunch of architecture simulators that are simulating the architecture instruction set with different models. And then you run all those simulations in another supercomputer, and then you actually have all the verification basically running before the step. So based on that, the experience to actually bring up the chips, and the chips work the first time in all these projects, most of the time fairly well. Maybe they were not perfect, maybe there is another release or 3 releases, but most of the time there was something that it was useful. And for example, in one project, we're actually able to boot Linux. Since the 2 days after we received the first chip, it was running Linux, and it's a new chip basically as well. The same thing, we're actually being able to run in 1,000 nodes in a month, basically running the whole applications basically on that setup. So that was basically like a fairly investment on our side. Usually the hardware guys can delay basically, and there's not really delay, but when the software actually show up, we're actually gated by the time to actually release some of the architectures. And just to mention a few things and basically like finish a few things on that one. The users were able to scale basically like these machines to very large sizes. When we actually did Blue Gene, the largest machine basically that we had existing was about 8,000 nodes. We built like 1 degree more of scalability on that side with more limited memory per node. In general, the scaling has been like not the biggest issue. Some applications did have problems. We had like a few cases that we were not expecting to actually like have problems. We actually show up. There was one case, for example, that the machine was not ready, right? One of the machines was not ready, and we gave it to the scientists for the weekend to try out, and they actually ran basically the whole simulation for a weekend. They got the output, and then they tried to run it in a visualization environment to actually see if the output was correct or not. The visualization, just reading the file, took about a week, basically, for the compute that was basically on the system. There was one thing that, we're doing basically graph partitioning, and the whole project was parallel, but the partitioning basically was not parallel at all. And you could not run that code on that machine because it was a serial component that needed to be parallelized. It would not fit on the node, and basically you need to actually write the codes basically in order to do it. But once you actually overcame some of these capabilities, the thing basically worked fairly well. The one concern we had, right? When you're actually building machines basically that are 100 racks, 100 refrigerators, would it stay up enough basically to actually do something useful, or that would be continuously on the rebooting kind of environment? And surprise, surprise, most of the machines stay up fairly well. Probably the fact that we had no low power, the fact that we had no state. We actually, if you see how the CS department managed basically its 200 or so workstations, basically here with a very small team. They only had 5 people to manage all the workstations, but they could only do it that because everything was uniform, everything was standardized, and there was no state in any of the nodes. Those machines were pretty much like that. We actually be careful not to produce any state that they will need to be able to move from one node to another one. Everything would actually be sitting outside, basically, on the machines too. Now, the part that we had the biggest trouble was on the compiler side. And we spent a ridiculous amount of money on compilation, right? We actually played, they have floating point units, and tried to use these floating point units and form efficiently automatically from the compiler. Almost no task. And there is a reason why it was my least favorite topic at Brown, basically, right? Compilers, on the things. It was really suffering to get that. You get the performance if you actually run runtime libraries and you actually get something that is tuned and assembly and for the things, but try to get the compiler still use these floating point units from a C language and from a Fortran language. It's still not an easy thing to do. It was really something painful for that. We tried to move the scientists to higher level programming languages. We spent a lot of effort as well on something that was high productivity, basically, right? Try to write languages like Extend or UPC, but very few scientists were comfortable with actually trying those higher level optimizations. They still have this code running in Fortran 77 that had been running it for the last 30 years, and it needed to run, and they expected us to give good performance from those nodes, and it was not basically something that it was easy for us to do. So just give you a quick overview of some of the things I actually have it. It's a pleasure to be here, and it's a pleasure to be with John, and I hope I show you some of the things that I learned here, how we actually map basically to the real world. Okay?